Welcome. Let's see distance or impedance protection in respect of transmission line, distribution line. Symbol representation of distance or impedance protection. As per ANSI it is denoted as 21. As per IEC 60617 it is denoted as Z. Here, Z equals R plus JX. Where Z equals impedance, R equals resistance, X equals reactance, it is measured in ohm. Where J represents imaginary component. Jx equals J inductive reactance minus J capacitive reactance, which are in same plane but in different direction. Here you can see source is feeding power to load through transmission line. Source impedance is less compared to transmission and load impedance. Fundamental reason is that source end system should be efficient. Here we will calculate current in case of fault at source end. Current equals voltage divided by impedance. At source end impedance is 2 ohm, and considering 132 kV system, current would be 66,000 ampere. Hence fault impact is very high at source end due to less impedance. Here we will calculate current in case of fault at transmission line. Current equals voltage divided by impedance. At transmission level, impedance is 20 ohm, and considering 132 kV system, current would be 6,600 ampere. Hence fault impact is less compared to source end, due to addition of source and transmission line impedance. Here we will calculate current drawn at load end in case of fault. Current equals voltage divided by impedance. At load end impedance is 200 ohm, and considering 132 kV system, current would be 660 ampere. Hence fault impact at load end is very less compared to source end, due to addition of source, transmission, and load impedance. For the impedance relay or distance relay, input required is current and voltage. Current can be fed from current transformer with protection class core, and voltage can be fed through voltage transformer with protection core. When power flow from substation A to B, resistive and reactive power will flow in forward direction, then impedance seen by relay in first quadrant. When power flow from substation B to A, resistive and reactive power will flow in reverse direction, then impedance seen by relay in third quadrant. When resistive power is flowing from B to A, and reactive power flowing from A to B, then impedance seen by relay in second quadrant. When resistive power is flowing from A to B, and reactive power flowing from B to A, then impedance seen by relay in fourth quadrant. So, in case of forward direction power flow, impedance seen by relay in first quadrant, this is usual scenario. And in reverse direction power flow, impedance seen by relay in third quadrant, this scenario may occur sometimes. Now let's see various characteristics of impedance or distance relay. This is mho characteristics. This characteristics has a radius, which is set to a fixed ohmic value. We can change characteristics by changing ohmic values. This is offset mho characteristic. As we need to monitor characteristics, in first quadrant, we have shifted mho characteristics as shown. This characteristics covers most of the values of fault impedance. However, in case of 100% fault impedance, value may occur outside of characteristic, due to the error in current and voltage input. Hence it is advisable to have protection of 80% of line length and keep 20% margin. Outside the zone relay will not operate. There are various characteristics have been developed to see impedance as per protection requirements. This is quadrilateral characteristics. This is lenticular characteristics. This is elliptical characteristics. We can choose the correct characteristics, based on the actual line parameters that we are going to protect. Now let's consider radial feeder and put impedance relay at substation A. Now let's consider fault applied at 100% of protected line, resistance, and reactance will be seen. My relay is 100% as shown. Here fault is applied at 50% of line length, and impedance will be seen by relay would be 50%. Due to the higher reactance of line, characteristic angle generally seen is 60 degree. Here fault is applied at 30% of line length, and impedance will be seen by relay would be 30%. Here, there is change in characteristic angle, which is generally seen as 45 degree, it is reduced as we are moving towards source. Here fault is applied at 10% of line length, and impedance will be seen by relay would be 10%. Here, there is further reduction in characteristic angle, as line become more resistive. Characteristics should be such that, it should cover required values of impedance, and it is called protective operating zone. Impedance seen by relay within this zone, will give trip command to breaker, and outside zone, relay will not operate. Zone 1 will have 80% reach of total transmission line. Zone 2 is provided 120% of line length, to avoid unprotected zone of transmission system. Further, it will also overlap Zone 1, and also cover 20% protection zone of next line. Now let's consider scenario, fault occurred at 50% of line length as shown. As fault has occurred within 80% of line length, breaker will get tripped with 0-second delay. Now let's apply fault at 90% of line length. In this scenario, impedance relay will see fault in zone 2, and operate with time delay of 0.5 second. Here fault is applied within 20% of line from B. In this scenario, impedance relay will see fault in zone 2, and operate with time delay of 0.5 second. While impedance relay B will operate with 0-second delay. As impedance is inversely proportional to current, increase in load current will reduce impedance value, and impedance may fall of protective zone area of relay characteristics, and gives trip command, and relay may maloperate. To avoid this scenario, lenticular characteristics is used. Here distance relay is introduced at both end of line. Zone 1 and 2 coverage is shown for both end. Zone 1 covers 80% zone, while Zone 2 covers 120% zone. There is no communication between relays. If fault occur at 50% of line length, then both distance relay will see fault in Zone 1, and operate with 0-second delay. If fault occur at 10% of line length from A, then distance relay at A will see fault in Zone 1, and operate with 0-second delay. Still fault is being fed from B station, hence relay at B must trip breaker to remove faulty line. Relay at B, see fault in Zone 2 and operate with 0.5 second delay. Now let's consider bus fault has occurred at station A, and current will flow in reverse direction, so fault impedance will be seen by relay in third quadrant. Due to the bus fault, voltage becomes 0 and distance relay at A will operate. To prevent this, relays are provided with voltage memory function, relay record couple of cycles before voltage collapses, and if voltage is 0, relay will work out impedance value, whether it is in quadrant 1 or 3. If it's in third quadrant, relay will not operate, so relay prevented with out of zone fault operation. Here, communication link is provided between two distance relay. Communication circuit will help to speed up fault clearance between substation. In case of fault at middle of line, both relay will see fault in zone 1, and send zone 1 intertrip command to remote end. Both relay will operate with 0-second time delay. In case of fault at 10% from station A, relay at A will see fault in zone 1, and send zone 1 intertrip command to remote end. While relay at B will see fault in zone 2 and send zone 2 pickup command to remote end. Relay at A will operate instantaneously, as it has detected fault under zone 1, as the relay at B has received intertrip command from station A, it will also operate instantaneously without time delay. Now let's consider fault at busbar at station A. Distance relay at A will see fault in zone 3, and send zone 3 pickup command to remote end. Distance relay at B see fault in zone 2, as the relay at A seen that fault in reverse direction, and it is not line fault, it will be operated through busbar protection, as the relay at B has received intertrip command from station A, that is zone 3 operated, so relay at B will block zone 2 trip command, and will not operate. This is called blocking scheme. Communication circuit will help to speed up fault clearance between substation. Redundancy can be provided in case of failure of communication circuit. We will see differential transmission line protection next video. We will discuss pilot wire and fiber optic schemes for differential protection. Stay tuned. Thank you for your attention and time. More stuff coming soon. Don't forget to subscribe.